The National Electrical Code, specifically Article 392.10a, addresses cable tray fill requirements, and a key distinction is made based on conductor size, particularly when comparing 1/0 to 4/0 American wire gauge conductors with 250 to 1000 kc conductors. The underlying reason for these differences lies in the heat dissipation characteristics inherent to various conductor sizes and configurations. Smaller conductors, exemplified by the 1/0 to 4/0 American wire gauge range, exhibit a higher electrical resistance per unit length compared to their larger counterparts. This increased resistance directly translates to greater heat generation when the conductor is actively carrying electrical current. The fundamental principle at play is joule heating, where electrical energy is converted into thermal energy due to the resistance encountered by the current flow. Excessive heat buildup in conductors can precipitate several detrimental effects. Firstly, elevated temperatures can degrade the insulation material surrounding the conductor, potentially leading to premature failure and increasing the risk of electrical shorts or ground faults. Secondly, prolonged exposure to high temperatures can anneal the copper or aluminum conductor itself, reducing its mechanical strength and current carrying capacity. Thirdly, the accumulated heat can negatively impact the cable tray structure, potentially causing deformation or damage, particularly if the tray is constructed from materials sensitive to heat. To mitigate these risks associated with smaller conductors, the NEC mandates a single-layer installation within the cable tray. This configuration maximizes the surface area available for heat dissipation, facilitating convective cooling through the surrounding air. By arranging the conductors in a single layer, optimal air circulation is achieved around each conductor, allowing for efficient removal of heat generated during operation. This strategy effectively prevents localized hotspots and maintains the overall conductor temperature within acceptable limits, thereby ensuring the long-term reliability and safety of the electrical system. Conversely, larger conductors, such as those in the 250 to 1000 kc range, possess a significantly lower electrical resistance compared to the smaller conductors. Consequently, they generate less heat when carrying the same amount of current. This reduced heat generation profile permits a more compact installation configuration within the cable tray. Specifically, the NEC allows for the stacking of these larger conductors, provided they are not bundled together. The rationale behind this allowance is that the lower heat generation rate, coupled with the larger surface area of the conductors themselves, enables sufficient heat dissipation even when they are stacked upon one another. However, it's crucial to emphasize the stipulation that these larger conductors must not be bundled. Bundling multiple conductors together restricts airflow and impedes heat dissipation. When conductors are tightly packed, the heat generated by each conductor is trapped within the bundle, leading to a substantial increase in the overall temperature. This elevated temperature can negate the advantage of using larger conductors and create a situation comparable to or even worse than that of smaller conductors installed without adequate spacing. Therefore, the NEC mandates that bundled conductors, regardless of their size, must be installed in a single layer to ensure proper heat dissipation. The NEC requirements address various aspects of cable tray installation to ensure safety and performance. These requirements cover conductor spacing, support methods, and grounding techniques. Firstly, proper conductor spacing is crucial for heat dissipation and to prevent electrical faults. The NEC specifies minimum spacing requirements based on voltage levels and conductor sizes. Secondly, cable trays must be adequately supported to handle the weight of the cables and any additional loads. The support spacing should comply with the manufacturer specifications and the NEC guidelines to prevent sagging or damage to the tray. Thirdly, grounding is essential for cable trays to provide a safe path for fault currents. The NEC outlines specific grounding requirements based on the type of system and the materials used for the cable tray. In summary, the differentiation in cable tray width requirements outlined in NEC Article 392.10 for various conductor sizes is fundamentally rooted in the principles of heat dissipation. Smaller conductors, due to their higher resistance, necessitate a single-layer installation to facilitate adequate cooling, while larger conductors, characterized by low resistance and reduced heat generation, can be stacked, provided they are not bundled. These regulations are meticulously designed to prevent overheating, protect conductor insulation, and ensure the overall safety and reliability of electrical installations. These considerations extend beyond just the conductor size and encompass factors such as ambient temperature, conductor insulation type, and the presence of other heat-generating equipment in the vicinity. For instance, in environments with elevated ambient temperatures, the allowable ampacity of conductors may need to be derated to compensate for the reduced heat dissipation capacity. Similarly, the type of insulation used on the conductor plays a significant role in its ability to withstand high temperatures. Conductors with high temperature ratings, such as those insulated with cross-linked polyethylene, are capable of operating at higher temperatures compared to those with traditional polyvinyl chloride insulation. Furthermore, the presence of other heat-generating equipment, such as transformers or lighting fixtures, can contribute to the overall thermal load in the area, necessitating adjustments to conductor spacing and cable tray fill to ensure adequate cooling. Therefore, a comprehensive understanding of heat transfer principles and the specific environmental conditions is essential for the proper design and installation of cable tray systems. The process of heat transfer occurs through three primary mechanisms: conduction, convection, and radiation. Conduction involves the transfer of heat through a material due to a temperature gradient. In the context of cable trays, heat is conducted from the conductor through the insulation and into the surrounding air or the cable tray structure itself. Convection, on the other hand, involves the transfer of heat through the movement of fluids, such as air. As the conductors heat up, they warm the surrounding air, causing it to rise and be replaced by cooler air, creating a convective current that helps to dissipate heat. Radiation involves the transfer of heat through electromagnetic waves. All objects emit thermal radiation, and the amount of radiation emitted depends on the object's temperature and surface properties. In cable trays, conductors radiate heat to the surrounding environment, contributing to the overall heat dissipation process. The relative importance of each heat transfer mechanism depends on the specific installation conditions. Conduction is typically the dominant mechanism for heat transfer within the conductor and insulation, while convection and radiation play a more significant role in dissipating heat from the conductor surface to the surrounding environment. The design of cable tray systems should consider all three heat transfer mechanisms to ensure effective heat dissipation. This may involve selecting materials with high thermal conductivity for the cable tray structure, providing adequate ventilation to promote convective cooling, and using surface coatings with high emissivity to enhance radiative heat transfer. In addition to heat dissipation considerations, cable tray installations must also comply with other NEC requirements related to mechanical protection, support, and grounding. Cable trays must provide adequate mechanical protection for the conductors they support, shielding them from physical damage. The trays should be constructed from durable materials and designed to withstand the expected loads and environmental conditions. The support system for cable trays must be designed to provide adequate support and prevent sagging or deformation. The spacing between supports should comply with the manufacturer's recommendations and the NEC guidelines. Grounding is essential for cable trays to provide a safe path for fault currents. The grounding system should be designed to minimize the impedance to ground and ensure that fault currents are safely dissipated. The NEC specifies detailed requirements for grounding cable trays based on the type of system and the materials used for the tray. Compliance with all applicable NEC requirements is essential for ensuring the safety and reliability of cable tray installations. Proper design, installation, and maintenance of cable tray systems are crucial for preventing electrical hazards and ensuring the long-term performance of electrical systems. The specific requirements outlined in NEC Article 392.10 are intended to provide a safe and effective means of installing conductors and cable trays, taking into account the heat dissipation characteristics of different conductor sizes and configurations. By adhering to these requirements, electrical professionals can ensure that cable tray installations are both safe and reliable,